In this lesson, we're going to be talking about one of the most important aspects of mathematics, algebra, calculus, trigonometry, and that's referred to as functions. Now, we're going to be learning in college algebra numerous different types of functions and their graphs and so on. But before we can do that, we have to get some terminology down and we have to get the general idea of what a function is. So let's take a look at one representation of a function. First one is just a representation referred to as a table. And this here describes temperature at Chaffey College at different times throughout the day. So let's say that we started our stopwatch at 8 o'clock a.m. We would say that that would be t equals 0. Okay, that would be our input of a time. If t is equal to 6, then that means that it's 6 hours after 8 o'clock a.m., and that's now 2 o'clock p.m. And so look at what the table is showing. It's showing us that at 8 o'clock a.m., the temperature was 58 degrees. And throughout the day, it appeared that it started to increase in temperature, but then it decreased again for a little while until it reached 4 a.m. the next day, and then it started to increase again, it looks like. This is referred to as a function. But there's a reason why it's a function. We have to describe why is this a function and certain other tables may not be. So first of all, we could display this data in a table, the data from the table in a set of ordered pairs, where the input or the time is referred to by an x coordinate or the first component, while the temperature is our y or our second component. So this could be listed now as another representation of a function. Now, we haven't learned why this is a function yet, so let's just go ahead and recognize that what this really is called a relation. So a relation is just a set of ordered pairs, and sometimes a relation is referred to by a table, sometimes it's referred to by a graph. But notice that we call it a relation because it's showing a relationship between an x coordinate and a y coordinate. So in particular, a relation in which every input, which would be a time, gives me exactly one output, which would be a temperature, is referred to as a function. It's a very particular type of relation, and it's really important that we understand and then say this mantra over and over. A function implies that every input, or every x, gives only one output or only one y. So let's take a look at why and if a function is so important. I mean, if we take a look at the above scenario here, we know that it describes a function because we're saying every time gives me only one temperature. For instance, it's not possible that it's 68 degrees and 85 degrees at 2 o'clock p.m. Okay, now obviously in different parts of the world that could be true, but if we're standing in one spot, I can't have two temperatures at the exact same input of time. Now, some may be thinking, right, but I see that 54 degrees showed up 2 times. But that's still a function because we're saying at 1 o'clock a.m., the temperature was 54, and at 6 o'clock a.m., the temperature was again 54. So each time gave me a single temperature. Now in this example, the temperature depends on the time of day. So we refer to the temperature as the dependent variable, while we refer to time as the independent variable, because we can just choose any random time, but whatever time we pick, the temperature depends on the time that we chose. So in an ordered pair, what we can recognize is that the independent variable goes first, which is why we refer to that as x, while the dependent variable goes second, which is why we refer to that as y. We could also think of this in terms of alphabetical order. So if we now take a look at some examples here, let's look at a few different relations. So let's take a look at this relation and determine whether or not it's a function. Remember the mantra. Every input must give only one output. Well, we should take a look at all of the blue values and recognize that because they're all unique, 2 gives me a single output, 3 gives me a single output, 0 gives me a single output, and so on. So yes, this is a function because each x goes to only one y. But let's look at how we can modify this relation by just picking one more point and see why this is not a function. If you recognize now, the reason this isn't a function is that in this ordered pair, 3 gives me the output of -7, while later on, 3 gives me the output of 2. That means that 3 gives me 2 outputs, and therefore this is not a function. So we could look at a relation in a different way. This little grouping of bubbles is referred to as a mapping. And we want to determine whether or not the following mapping is a function. So let's look at all of these arrows that are connecting x coordinates to y coordinates. All of the x bubbles on the left, all of the y values on the right. And notice that each of these x's, -17, gives me an output of 3. -1 gives me an output of 7. 0 gives me an answer of 0, and so on. So this is a function because every single x only has one arrow coming out of it. Every x is only going to one y. Now, some people look at this and say, well, what about 7 over here, though? I see that -1 gave me 7, and 4 also gave me 7. So wouldn't that mean that this isn't a function? But that would be the opposite of what we're looking at. That would mean that one output came from 2 inputs, and that's not really what our situation is. But let's look at one example of how we could modify this. What if we had 4 with another arrow coming out of it? Now that would mean that 4 gives me an output of 7, but 4 also gives me an output of 10. So since the input of 4 gives me 2 outputs, again, that is not a function. Let's look at one last example here. One other representation of a function, similar to the prior page, was a table. Notice that every x or every input gives me a single output, and therefore, yes, this is a function. But what if we modify this again by creating one more ordered pair? You might notice that these are the same values that we had in this original table, or a few of the same values, 2, 4, 3, -7, 0, 4, and so on. But now we have one more point where the input of 3 gave me -7, but then later on, 3 gave me an output of 2. In this case, that would not be a function. So we've seen a few different types of ways to represent a function. We looked at a set of ordered pairs, we looked at a mapping, we looked at a table. But I'd say the most common representation of a function is an equation or a graph. And we're going to take a look at both of those now. So if we take a look at an equation, what if I ask, is y equals 3/4 times x minus 2 a function? Well, remember, in order to be a function, and we're going to learn a lot of different types of equations, but in order to be a function, every x that I choose has to give me only one y value. Okay, well, if that's the case, then the reason this is in fact a function is that no matter what I choose to plug in for x, when I multiply by 3/4, I'm only going to get one answer. When I now take that answer and subtract 2, that's still only going to give me one single number. And therefore, without choosing specific values of x, anytime we multiply a number by 3/4 and then subtract 2, that's always going to give me one single output. So now let's take a look at what the graph of this looks like. This is in the first few lessons that you learn when you learn about functions, but this is in fact what we refer to as a linear function because the graph of it will be a line. Now, the reason why this graph is a line is because every time we plug in a single input, we obviously get a single output. And notice no matter what input represented by that red line we choose to plug in, notice that it's only giving me one output. Notice that it's following along, giving me one single y value at every single input that I choose. And therefore, if we take a look at that one more time, the x-axis is our horizontal, which means anytime we choose a certain x value, I can see that the output is a y value. If I choose this x value, I get an output of this y value here. But notice that when that red line passes along, it's only touching the graph at one point. We refer to that as the vertical line test. The vertical line test tells us whether a given graph describes a function. And because that vertical line only touched the graph one time at every single input, this represents a function. Therefore, if we were to draw a circle on this graph, that circle would not be a function because a vertical line would cross through at multiple points, at 2 points. So I often think about a function as being a machine of some kind. And so let's think about this machine. A machine's job is to take some input, maybe the machine's job is to take aluminum, and to do some task to it in order to turn it into an aluminum can. Or perhaps take a piece of plastic, do something to it, and all of a sudden it becomes a mechanical pencil. So notice that if we think about a machine, the machine will basically just take some input, which in a situation like this, let's just say that we have this equation, y equals x squared minus 3x plus 4, and we want to determine whether or not that describes a function. So what we're doing here is that we're taking an x value. Okay, we'll call this, let's just first of all call this machine by a certain name. The name of this machine, we'll just call it machine F so we know what we're referring to. I'm now going to take an input, which is called x. Well, x is always the input. And we're basically saying here, if I plug in a single x value, and let's not pick a particular one, but you can think about maybe I choose x to be 2. Will I only get one output of y? Well, let's see what this machine will do to that input. This particular machine will take that input of x, it'll square it, then it'll subtract 3 times that same input, then it's going to add 4. So when I take that input, square it, subtract 3 times the input, then add 4, this is what we refer to as the function rule. The rule that that equation is telling me to do to the input. And when I do that, my output's going to become y. And therefore, what we should recognize about this is that every input is going to give me just a single number output. And not only do we know it's a function, but we can now have a new way to show that it's a function. And the way that we can do that is by naming the equation. Instead of y equals, we're going to refer to it as f of x. F of x. And so now the beauty of this notation is that if you ever see f of x, we don't have to wonder or check or guess whether or not this represents a function. We'll know it's a function because it says it's a function. But it also has a few different benefits to put it in this notation. Okay, one benefit is that it's now naming this particular function rule. It's now naming the rule that says to square an input, subtract 3 times an input, and add 4. Not only that, it tells us the value that we're plugging in. Okay, and so this value right here would maybe be a 1 or a 3 or a -2. And finally, this whole quantity on the right side is referring to the set of rules that will give us our particular output. So in other words, what it's telling us is what to plug in, where do we plug it in, and when we do so, what exactly are we going to get out? Let's take a look then of how to evaluate a function at different inputs. So let's just take that same function that we just saw on the previous slide and now try to evaluate each of these quantities. So let's get in the habit of reading them correctly. This would be referred to as f of 3, which simply means to take 3 and use that as the input. Here we have f of -2 and f of 4a. So if we start with f of 3, notice that all that means is we're going to replace each of the x values with 3. But where are we going to plug it in? We're going to plug it into the equation that we're calling f, or in other words, f of x. So that means on the other side, we're just simply going to plug 3 in for all of the inputs and simplify. Notice that 3 squared is 9. 3 times 3 is also 9. 9 minus 9 plus 4 gives me an output of 4. And now the beauty of this notation is saying that if f of 3 equals 4, that means when I go to the function named f and replace the input with 3, my output will become 4. Let's take a look now at what happens when we use f of negative 2. Well, it's going to be the same idea, except that now we're replacing all of the inputs with negative 2. And we're applying the order of operations again. Negative 2 times itself is 4. Negative 3 times negative 2 is positive 6. So when I now add these results, I finally get an answer of 14, which again simply means that if I go to the function named f and replace the input with negative 2, my output will become 14. But now notice that we're not only able to plug in numeric quantities, maybe we could plug in algebraic expressions as well, or variable expressions. This means the same thing to say f of 4a is just telling us again that 4a is the input. So when I take 4a as the input, that means to replace each of the inputs or each of the x's with 4a. Notice how every time we're doing this, we're putting it in parentheses in order to make sure that the parentheses applies to all of the operations. So 4a times itself gives me 16a squared. Negative 3 times 4a gives me negative 12a. And finally, when I add 4, I know I'm done because none of these are like terms. I can't combine them because this has an a squared type of term. Here we have an a type of term. And finally, we have a constant. So what you should recognize is when we plug in a variable expression, we're often going to get out a variable expression. So we've seen many types of different representations of a function, whether it be a table or a list of ordered pairs or a mapping or an equation or even a graph. But each of those representations is telling us the same thing. Does every input give me exactly one output? Now, there are two important aspects of a function that a lot of students have issues with at times, but they're referred to as domain and range. And when we talk about the domain and the range of a function, we're simply referring to all of the inputs that we could plug in and all of the outputs that we can get out. So when I refer to the domain of a function, that's just simply telling me what inputs can I plug in and still get a y value. What am I able to plug in for x and still get an answer? The range is kind of the opposite. It's telling me the set of all the outputs that came from plugging in each of the inputs. So don't just say domain is x and range is y. Instead, recognize that the domain is telling us everything we're able to plug in, while the range is telling me everything that I'm able to get out. So we often will think about the domain of a function as just being all real numbers, meaning we can think of any number to choose and I can plug it into a function. Unfortunately, that's not always true. There's a lot of times where we have some restrictions, some values that when you try to plug them in, you don't get an actual answer. And so there's normally, and there will be more throughout the course, but normally we should recognize that we're not allowed to divide by 0, and we're not allowed to take the square roots of negative numbers. So let's take a look at the dividing by 0 component here. In order to find out what would cause me to divide by 0, that would mean that we would want the denominator to be 0. So let's find the values of x where the denominator is 0. Well, in this problem right here, that would just mean where is x minus 3 equal to 0? Well, that's obviously going to be when x is equal to 3. So we should realize that this is the only value that will not give me an answer. If you try to plug in 3 to this function, notice we get 4 over 0. which is undefined. Be careful, that's not equal to 0. So notice that when I write the domain, we would typically think of the domain as being all real numbers, which would be negative infinity all the way to infinity. So remember that this is referred to as interval notation, which just basically says that I can plug in anything from negative infinity to 3, but I'm not allowed to plug in 3. Because I can't plug in 3, I put a parentheses on it. And then I use the union symbol to demonstrate that there's more answers that I could plug in. And then notice that I start at 3 again with another parentheses. So this would be the domain of this function. So we start by thinking I can virtually plug in almost anything. The one problem is that I can't divide by 0. There's a second type of restriction as well, which is taking the square root of a negative number. It makes no sense. We know that the square root of 9 is equal to 3 because 3 times itself gives me 9. But it doesn't make sense to take the square root of negative 9 because nothing can multiply by itself to give that negative number. So what we do is, in order to find the domain of this, is that we need to make sure that this quantity inside the radical or inside the square root is not negative. So why don't we go ahead and find out, when is 5 minus x greater than or equal to 0? That's what it means to not be negative. When is this quantity on the left greater than 0, which means positive, or where is it equal to 0? Well, if I solve this, then that means that x would have to be less than or equal to 5, which means if I want to write this as interval notation, we need to realize that it's any number before 5. Or in other words, any number from negative infinity all the way to 5. So we put negative infinity, comma 5. But notice that it's allowed to equal 5. Up in the first example, it was not allowed to equal 3, which is why we put a parentheses on 3. But if it's ever allowed to equal that particular quantity, then notice that I could put a bracket on it and therefore get negative infinity to 5. So we've learned a bit of the terminology and a bit of the features referring to a function, but keep in mind that in order to be a function, every input should give me only one output. And now looking at domain and range, we may have a lot of different inputs, which we refer to as the domain, that will yield various outputs, which is what we refer to as the range.